Hello everyone. In the first part of this review, I will quick review how to store in numbers in a computers. And for the second part of this video, I will talk about the Horner's method. As a general, on a computer, numbers are stored in binary format, not in a decimal format. Okay, it's meaning for storing a number on a computer, we are using 0 and 1. There are two types of the number we store and manipulated in our computations. The first one is called fixed point, that is related to integer number, like as 39. Okay. The second type of numbers is called floating point. This is for real number, such as 39.8, 11.9. Okay, this is the two category for storing a number on a computer. First, we start how we can store the integer number on a computer. Okay, for storing an integer number on a computer, first we have to convert the decimal numbers to the binary format. One of the examples, for example, we have this integer number 39. This is as a base 10, or it's called as a decimal numbers. How we can convert to the binary as a base 2, we have to divide the number, this decimal number, to the number 2. This is 19 plus 1. This is as a remainder, and this is as a quotient. We divided the quotient to the 2. This is become 9 plus 1. Again, this is the remainder for these divisions, and this is as a quotient. 9 divided 2 is 4 plus 1, and 4 divided 2 become 2 plus 0, and 1 divided 2 is 0 plus 1. Once the quotients of the division, okay, reach to the 0, is meaning we have to stop the continue this division, okay? And now we can convert this decimal number to the binary, and how we can read and write this number from bottom to up, okay? For this reason, the binary of the 39 will be 1, 0, 0, 1, 1, 1. Okay, this is about converting the decimal to the binary. And again, once the quotients of the division reach to the 0, it's meaning we have to stop the algorithm. Okay, and we completely convert this decimal to the binary format. And how we can check this conversion is correct. Okay, for checking, when we are working with the integer number, the first bit from the right side is a 2 to the power 0, 2 to the power 3, 4, and 5. Okay, if we write 1 times 2 to the power 5, 2 to the power 2, if we calculate, this is 32, this is 0, this is 0, this is 4, 2, and 1. Okay, when we add it together, the answer becomes 39. Is meaning this binary number is represent the number 39. Okay. Once we convert the fixed point or integer number to the binary format, now we have to know that how to store this number or fixed point number on a computer. As a general, for storing the fixed point in a computer, or have a two options. Okay, this is a fixed point. We have two options. The first option is called single precision. For the single precision SD, okay, and the integer uses 16 bits, okay, and the first bit, see, this is the 16 bits. The first bit from the left side, okay, is called sign bits. What's the meaning? For example, if our number is a positive or negative, okay, we have to define for the computers, okay? How we can, what is this number of the positive numbers, okay, or negative number? We have this equation. For the sign, we have -1 to the s. If the s as a 0, okay, is meaning if the 0 is a first number in the first bit, okay, it's meaning our number is positive. If the number in the sign bit as a 1, it's meaning this is represent the negative number. Now we have a 15 bits, okay, for storing a number on computers. And the largest single precision integer that the computer can write is plus minus 32 767. And if I draw, this is minus 32 767 767. Okay. If the decimal numbers that you have in this range, the computer can store exactly on a computer. But if you are attempting to store a number larger than these two values, what's happened? For example, if I try to store any number beyond this value, okay, we will get the error, and this is called integer overflow error. Okay, and this is as a fatal error. Again, this is as a integer overflow error. How about this next type of the fixed point? The next type of the fixed point is a double precision. For double precision, okay, the integers uses 32 bits, okay, and look as the single precision, the first bit from the left side is about the sign bits, and 31 bits used for storing a decimal number on a computer. Okay, and the largest number for double precision of the integer or fixed point number is 2,000,000,483,647. This is approximately as a 2 GB. Wait again, gigabytes is about the capacity of the memory. Okay, but this number is very close to 2 GB. Okay, and if this is again, this is the largest number for double precisions. And if I draw this line, if you are attempting to write any number larger than these two value, is meaning 2 GB, okay, what's happened? You will get error, and this is called integer overflow error. That is the bit. Okay, but it's very important. This overflow error is related to the integer number. This is about the summary of the first type of the numbers, that is as an integer number. Okay, for the fixed point or as an integer number, we have a single precisions, and the computer use 16 bits, and this is about the largest numbers that we can store on a single precision of the integers. And if you are attempting to write any numbers larger than this value, and you will the system give you the error, and this is called integer overflow error. For the double precision error, this is the largest number that we can store on a computer, and 32 bits. Okay, the integer numbers uses for double precisions. The second category or the second type of the numbers is a floating point or the real numbers. Okay, before I talk about the real numbers, okay, based on these two graphs, okay, we can say any integer number except 0 within this range can be written exactly on a computer. But if 0 is a declared integer and only integer arithmetic is used, then 0 is exactly written on a computer. But how about the real number? For real number, mostly we cannot store the real number exactly on a computer. First, we see how we can convert the decimal number, the fraction part, to the binary format. For example, if the fraction number that we have is number 0.9. This is as a base 10. And now we try to convert to the base 2. For converting the fraction part to the binary format, we should multiply this number to the 2. Is 1.8. We keep the integer numbers and we work with the fraction part. 0.8 times 2 is the 1.6. Again, we keep integer part and just working with the fraction part. See, when I gonna continue this process, okay? See, this part repeat again. For this reason, if if we continue, this cycle will be repeat and repeat, okay? And this is the answer of the binary format for this fraction number, okay? For reading the fraction part is the opposite of the integer part. We should read from the top to the down, okay? And just we read the integer part, okay? For this number, we have a 0 point. This is the binary point. And this is as a decimal point, okay? Is a 1, 1, 1, 0, 0, again repeat, 1, 1, 0, 0, 1, 1, 0, 0. And this is go to the infinity. And as we know that, okay, and we have a finite environment for all the computational devices, okay? For this reason, we have to stop these numbers at some point. It depends. For example, if we are using 7 bits for storing these numbers, okay, we have two approach. Using 7 bits, we have one approach is chop, another one as a round. For the chop, 1, 2, 3, 4, 5, 6, 7. Just cut the number. How about the round? For the round, always we have to look at a number after, for example, for this example, after the 7 bits. If the numbers after the cutting is 0, we get same number like as the chopping. But for example, if we are using 5 bits for storing this number on a computers, what is the number based on the chop and round? For the chop, 1, 2, 3, 4, 5, okay? And just chop. 1, 1, 1, 0, 0. But how about the round? We learned that when we are doing the rounding, we have to look at a number after, for example, after the 5 bits. What is the number after the 5 bits? Is a 1. We have to bring this number to here, okay? And as you can see, in the 5th bits, the number as a 0. For this reason, the answer becomes 0.11101. How about if we are using the 6 bits for storing these numbers for chop and round? See, for the chop, just count it. 1, 2, 3, 4, 5, 6. Is meaning we should cut a number after the 6 bits. 1, 1, 1, 0, 0, 1. This is the answer of the chop. But how about the round? We learned that for the rounding, we have to look at a number after this place, okay? What is the number after the 6 bit? Is 1. We should bring here. As you can see, the bit and the bit 6 is full with 1, okay? And we cannot store it. This bit, this number, turn to the 0, and both of these number move to the next bit, okay? And this bit become 1. Sorry, this one become 1. And if I write this one, we have 0, 1, 1, 1, 0, 1, 0. This is about the chop and round. For some condition, when we convert or when we constitute these numbers to the decimal conditions, the chop and the round give the same value. But how about these two conditions? Okay, the chop and round is different, okay? And when we convert this binary number to the decimal, the round number, okay, is larger than the chopping number. Because for the rounding, again, we have to look at a bit after the place that we are cutting in numbers. Okay, but how about the chop? We don't care about the bits after the using the bits. This is about converting the fraction part to the binary, okay? And now we try to understand how we can store the fraction or real number on a computer. Okay, if you remember, I mentioned when we talk about the real number, is meaning we are talking about the floating point. Okay, for the floating point, like as the integer numbers, okay, we have a single precision and double precisions. Okay, this is the floating point, that is real number. We have two condition, or we have two types or two precision for storing a real number on a computer. For the single precision, the real number uses 32 bits. Okay. The first bit is called sign bit. Again, it shows the number is positive or negative. 8 bits for characteristic and 23 bits for mantissa. Now we are trying to find the smallest number and the largest number that we can store for the single precision of the floating point number or real number. The smallest number for the single precision corresponds to 0 in all the bits for the characteristic and the mantissa. For this reason, the smallest number for single precision is plus minus 10 to the power 38 minus. Okay, and how about the largest number for the single precisions of the real number? The largest number corresponds to 1 in all bits in the characteristic and the mantissa, okay, and the value becomes plus minus 10 to the power 38. And if I draw this one, okay, this is minus 10, 38. we can store any number in this range. But how about this part and this part? Okay, if you are attempting to store any number smaller than these two values, the system reset to the nearest any of these numbers. Okay, that is called, this area is called real underflow error, that is as a non-fatal. Again, this is, we should mention, this is real underflow error. This meaning we are talking about real number, not for the integer number. How about these two area? This is called overflow error or real overflow error, that is called as a fatal. And we can say for all the real numbers, we have two conditions, underflow and overflow. When we are attempting to store any numbers in this range, okay, the computer will reset your number to one of the nearest these two numbers, and you will get the real underflow error. But how about these two areas? If you are attempting to store any number larger than these two values, okay, you get real overflow error. This is about the single precisions of the floating point. Has a 32 bits. This is about smallest number, and this is about largest number that we can store for the single precision. Also, the machine epsilon, okay, for single precision, approximately as a 10 to the minus 7, okay? And the next category for the next precision for the floating point number is double precision. For double precision, real number uses 64 bits, and again, the first bit from the left side is called sign bit. Eleven bits for the characteristic, and 52 bits for the mantissa pods. Okay, the smallest number that we can store for the double precision of the integer number is correspond to 0 in all bits in the characteristic and mantissa, and is approximately is plus minus 10 to the minus 308. How about the largest number? The largest number corresponds to 1 in all bits in the characteristic and mantissa, okay? And this amount, okay? And if I draw this one, okay, minus 10, this blue range as you can see, if you have any numbers in these two blue range, you can store on a computer. But if you are attempting to store any number smaller than this value, smaller than these two value, okay, what's happened? You will, the computer reset to the nearest of these numbers, okay, maybe as the minus 10 to the minus 308 or the positive of the 10 to the minus 308. And we have a real underflow error. Real, again, it's very important, real underflow error. And is non-fatal. But if you are attempting to store and write any number larger than these two values, what's happened? The real overflow error is happened for both sides, okay? And this is called fatal error. This is about the double precisions for the real number or the floating point number, and the epsilon of the machines for the double precision is 10 to the minus 16 because we are using the 64 bits, okay, for double precision. This is the summary of the first part of these lectures. Now I'm going to talk about the Horner's method. As a general, we know that the round-off error as an inherent error for all computational devices, okay? And it's a difficult, if not impossible, to control round-off error in a general. Round-off error is in general randomly distributed over our computations, okay? And we can say the round-off error is proportional to the epsilon of the machines, okay, and the number of the floating point operation, okay. We can control and the radius of the errors if we are, for example, using the double precisions, okay, for epsilon of the machines and try to reduce the number of floating point operations. Horner's method is a one method, okay, that we can use for evaluate the polynomials function. And when we are applying the Horner's method, okay, we can reduce the floating point operations in the polynomial function. For example, look at these polynomial functions. If I want to count the total floating point operations for these functions, as you can see, we have a 10 multiply operations and 4 adding, okay, between each parts, okay? For this reason, we have the total floating point operations for this function is 14. Now by nesting, we can reduce the floating point operation. And the floating point operation for that function, okay, become 8, okay? And by nesting, we can say we can reduce the floating point operation and reduce further adding, subtracting large and small numbers. That is another source of the arithmetic another source of the arithmetic for the round-off error. For this reason, what is the Horner's method? Okay, we learned that by Horner's method, we can control and reduce the floating point operations, okay, and is the algorithm for polynomial evaluation. And alternatively, Horner's method also refers to a method for approximating the roots of polynomials function. How this algorithm is working. For applying the Horner's method for polynomial function, first we have to write all the coefficients of these polynomial function from the highest to the lowest order. The highest order for this function is 4, and a sub 4 represent the coefficient for this order. We have A4, A3, A2, A1, and this is about the constant value. And now we are trying to find the value of this polynomial function at the x0. How the algorithm is working, first we write the highest order of the coefficient of the highest order, then multiple to the x0 and write here, and then we are adding to the next coefficient. Okay, the next coefficient is the a sub 3. Okay, and we get this answer, and again we multiply the whole of these terms to the x0 and write here and add to the a2. Okay, and we continue this all these steps until we reach to the constant value. Okay, and this part is called remainder of the Horner's method. Okay, and the remainder is showing the value of the polynomial function at the x0. Let's look at one example, okay, for that try to show how to apply the Horner's method. We have this polynomial function, and now we are trying to apply the Horner's method, okay, to find the value of this polynomial function at the x equal minus 2. For applying the Horner's method, let me write the equation. We have these polynomial functions, 2x4, 3x2, 3x minus 4. We should find the value of this polynomial function at minus 2. Based on the Horner's method, first we have to write all the coefficients of these functions from the highest to the lowest. The highest order for this polynomial function is 4, and this is the coefficients of this term. This is 2. How about the coefficient for the next order, is meaning x cubed? For this problem is 0. We have to write it. The next order is 2, and minus 3 is a coefficient. Okay, after that, this is the next coefficient, and the last one is minus 4. Again, this is the coefficient A4, A3, A2, A1, A0. And this is the point that we are trying to evaluate the function. First, we write the 2. 2 times minus 2 become minus 4 plus or add to this coefficient. What is the value from minus 4? Again, minus 4 times minus 2 become a, and we are adding to these coefficients. The value is 5. 5 times minus 2 is minus 10, okay? And we are adding to these coefficients, and the value is minus 7. How about this one? We have minus 2 times minus 7 plus minus 4, and the value is 10. Okay, this is about the Horner's method. What is this part? The first cell from the right side is showing the remainder in the Horner's method, or remainder for polynomial function. And we can say the value of this polynomial function at minus 2 is equal to this remainder, okay? And how about this part? This part is talk about the quotients of these polynomial functions, okay? And if I try to write it, okay, we have the quotient of these divisions, okay, is 2x cubed minus 4x squared plus 5x minus 7. This is very important, okay, and it will, and later I will show you. By these equations, we can find the first derivative of this polynomial function. Again, when we are using the Horner's method, you can find the answer of the polynomial function at any points, okay? And and by this algorithm, we can control the floating point operations. Always this remainder is showing the value of the polynomial function for that point. Okay. This is the example that I have already shown you, and this is the answer of this polynomial function. And also you can plug the minus 2 to these equations, okay? And when you solve it, you get the same answer, okay? And by using the Horner's method, we can find the first and the second derivative of the polynomial functions, because the Horner's method is related to synthetic division. Okay, if we divide the polynomial functions to x minus x naught, we will have this one. This is called quotients, and quotient always one order less than the polynomial functions. And this is as a one outcome of the Horner's method, and this is as a remainder. If I multiply the whole of these equations to the x minus x naught, okay, we get this equation, okay? And if we are trying to find the value of the polynomial function at the x naught, and when we apply the Horner's method, if the remainder of the algorithm becomes 0, it's meaning the x naught as a one roots of this polynomial function, and we can say the quotients contains other roots. But if the remainder of the Horner's method is not a 0, we can say the x naught is not a root of these polynomial functions, and the value of the polynomial function at the x naught is equal to the remainder of these functions. As a general, the Horner's method has a two outcome, okay, is we can find the quotients or we can measure the quotients of the polynomial function. And also we can find the value of the polynomial function at the x0, and the remainder of the Horner's method is represent the value of the polynomial function at any arbitrary point, like as x0. How we can, because we learned that by Horner's method, okay, we can find the value of the first and the second derivative of the function, polynomial function. This is our polynomial function that we have. If I take a derivative from these functions, okay, what is the derivative? Is a q prime x minus x naught plus qx. And if we evaluate this derivative of the polynomial function at the x naught, the value of this one is equal the quotients of the value of the quotients of polynomial function at this point, okay? And you can easily find the first derivative of the function based on the quotient. But if we take a derivative from this equation and find the second derivative of the polynomial function, we have these equations. And if we are trying to evaluate the second derivative of the function at the point x0, the answer of the second derivative of the polynomial function at the x0 is equal to q prime x0. This is about the first and the second, finding the first and the second derivative of the polynomial function by applying the Horner's method. What we can say, okay, for example, in this example and next example, I try to show and try to find the derivative of the polynomial function based on the Horner's method. Look at these polynomial functions. The highest order for this polynomial function as a 2, okay, we try to write all the coefficients from the highest to the lowest order. We have a2 related to the x squared, a1 for the x, and this is as a a0, as a constant value. We apply the Horner's method, okay, at the x0, okay, and this is as a remainder. If you remember, the first cell from the right side is called remainder, okay, and this value is showing, the remainder is showing the value of the polynomial function at the x0. How about this part? This is about the quotients of these equations, okay? And how we can write a2x, okay? Because the quotient always one order less than the polynomial function. What is the order of this polynomial function? Is 2. Okay, for this reason, one order less than the 2 is a 1. We have a21x plus, this is as a constant, a1 plus a2x1. This is the quotient of this equation, and if we are evaluate this quotient at the x0, okay, the answer is a1 plus 2a2x0. Okay, and if I try to take a derivative from the polynomial function, okay, what is the derivative of this polynomial function? Is a 2a2x plus a1. And if we are evaluate this polynomial function at the x0, we get same answer. For this reason, by Horner's method, we can evaluate the value of the function, first and the second derivative of the polynomial function. Let me to show you one examples, okay, for this algorithm or this method. Okay, look at these equations. Okay, we have this polynomial function. Okay, is 2x cubed minus 5x2 plus 3x minus 1. We should find the value of this polynomial function at point 2, the first derivative at point 2, and second derivative at point 2 by applying the Horner's method. The highest order for this problem is 3, okay? And now we have to write the all the coefficients from the highest to the lowest order. We have 2, the next one is minus 5, 3, minus 1. Okay, this is the point that we have to evaluate our polynomial function. Based on the Horner's method, first we write the 2. 2 times 2 become 4, and we add it to here is a minus 1. Minus 1 times 2 is times to the points that we are trying to find the value of the functions, plus 3, the answer is 1. 1 times 2 plus minus 1, the answer is 1. We learned that the last cell or first cell from the right side, okay, is called remainder, and it shows the value of the polynomial function at that point. Okay, and if I want to check this answer based on the mathematics, okay, if I plug number 2 to main equations, we have q minus 1. And when we solve this equation, the answer will be 1. Okay, this is about first part. This part is called quotient, okay, for this polynomial function. We learned that the first derivative of the polynomial function at point x0 is equal the value of the quotient at the x0. It's meaning if I try to find the value of this quotient at the x0, okay, we can find the first derivative of this polynomial function. Okay, evaluate at the same point. 2 times 2 is 4, plus minus 1 is 3. 2 times 3 is 6, plus 1 is 7. We are not going to work on a remainder when we are trying to find the first derivative, okay? Because based on this equation, we have to find the value of the x0 at the quotient equation, okay? This is the remainder for the quotient, okay? And we can say the value of the first derivative of this function this polynomial function at the 2 is equal 7. Let's check with the mathematics. What is the derivative of the first derivative of this polynomial function is a 6x squared minus 10x plus 3. If we are evaluate at point 2, the value is 7. See? 7, 7. At 2 is equal Q 7. This is about the first derivative of the polynomial function. Also, we can find the second derivative of the polynomial function based on this equation. It's meaning if we run the Horner's method for this answer, okay, we can find the second derivative of the polynomial function. Again, this is the point 2. 2 times 2 is 4 plus 3 becomes 7. Okay? And we can say if I multiply this number as a remainder, okay, to the 2, this number is showing this value of the second derivative of this polynomial function at point 2. Okay? Based on the Horner's method, is 40. Let's check with mathematics. This is about the first derivative of the polynomial function. And if we try to find the second derivative of this function, the answer is a 12x minus 10 at point 2 is 12 times 2 minus 10 is 40. See, 14, 40. Also, this is 40. Okay, this is about the Horner's method. And we learned that by Horner's method, we can control the floating point operations, okay, that is directly affect to the round off error, and the round off error become smaller or radius. There you can see the solution of this example on a notes. Okay, this is another example. Okay, we try to evaluate these polynomial functions at point 2 and also evaluate the first derivative of this polynomial function at the same point at point 2. The highest order is 3, okay? The coefficient as a 1, okay? And what is the coefficient for the x squared is 0. And this is the coefficient for the x, and this is the constant. If we write it and apply the Horner's method, the last cell is showing the remainder for this problem, and the remainder is showing the value of the polynomial function at that point. For this reason, the value of this polynomial function at point 2 is equal 7. And if we try to find the first derivative of this polynomial function based on the Horner's method, we have to run the Horner's method one more time. This is the 1 for the just for the quotient part. Okay, this is 1 times 2 become 2. 2 plus 2 is 4. 4 times 2 is 8 plus 2 is 10. Is meaning the first derivative of this polynomial function at point 2 is equal 10. And this is about the Horner's method. The Horner's method can be applied to complex arguments and also can be used to find for the first and the second derivative of the polynomial function. This is the end of introductory materials and the first chapter of modeling method.